Hello, and welcome to Old School Coding, where I pretend I'm back in 1991, working in C, producing a simulator for a microcomputer of that era. Specifically, I'm working in C99, which basically brought into the standard all of the practices that we were actively using in the 90s. And I am producing a simulation for a 8080 based microcomputer, which would have been a hobby system at the time. Specifically, I am looking at the documentation for Intel's MCS 80, which is the a little bit beyond hobbyist cost. I also have documentation available for the MSI 8080 and the Altair 8800, which will inform how I move forward on some of these things. So, we have done a whole bunch of things. Most recently, we managed to construct some operations that use three memory cycles. And I was looking at the list. I think the next thing to do is to do the jump instructions so we can actually have our test code do loops. Hey, why not? What I'm working forward toward eventually is being able to run code from the 80s and 90s on this simulation and have it work. I have a certain amount of CPM code. I've got the standard documentation from CPM on how to write a BIOS, and I have a copy of FigForth. So if I can interact with FigForth 8080 running on a simulated 8080, that will be this project. So what we see in front of us is the layout of what happens during each T-state for the instructions. And today we'll be focusing on the jump instruction, which is down here about the middle. And what we see is that it does the normal fetch cycle. It really accomplishes no work during T4. During T5, it's going to pick up the low byte of the destination address. And during M3, it's going to pick up the high byte of the destination address, and those go in the Z and W registers. These are not programmer visible, but they are architectural bits of the CPU. And then there's a note out here that during the next M1 cycle, WZ, that WZ register pair, will be used as the program counter. Now, I will be modifying that a little bit. So at the end of M3, where we've got the data in Z and W, at that point I will be latching WZ back into the program counter so we can use a standard instruction fetch cycle. The reason why I'm doing that is I'm looking to the future where we have a radically different kind of instruction fetch, the interrupt acknowledge cycle. I do not want to start duplicating that instruction fetch. I don't want to have, here's the instruction fetch, and now we're going to do a duplicate of it because we're jumping. And now we're going to take those two cases and we're going to duplicate it for another reason. I don't want to do that. I don't want to get a combinatorial explosion. So where I can eliminate that without causing any runtime penalty, I will. And how I'm going to eliminate it is that, yeah, here in the M3 cycle of all of these jumps, I will be copying ZW into the PC. Now, for the conditional jump, that means that this copy into PC has to know whether the condition is met or not. We're supposed to judge the condition way out here, which means I need to judge the condition and save that off somewhere. Now, maybe what I do is I do different M2, M3s. That might be the way to go. So we have an M2, M3 for jump and an M2, M3 for don't jump. That actually sounds best to me. At the end of it, if we're, the jump guy is going to go, we're heading to the PC, and the don't jump guy is going to say, oh, well, we loaded up Z and W, but we're going to continue onward with PC where it is. That opens out the call and return stuff. Actually, no, it doesn't. Call will be similar, but here in M3T3, where we've got the call address in ZW, before we do anything else, we do need to push the old PC onto the stack. And then here in M5, wow, M5, we will be copying the ZW into the PC. So we're going to keep that idea of move ZW into the PC during that last cycle. And for return, again, we're going to read from the stack into ZW, and we'll have to set it in the PC. So jump, call, and return are all going to share some of this logic. But let's start out with jump. In fact, I may do call and return and RST even in this same file so that they can share some of the code. I'll call it microcode. I didn't actually deal with any microcode until a bit later. Later in terms of I started dealing with the 8080 in the late 70s and early 80s, and my first run-in with microcode was at Color Scientific in 84, 85. I don't believe that the 8080 was microcoded. I think the 8080 was all discrete logic internally. But looking at this, it would be possible to design a modern chip implementing this instruction set and have it be microcoded. I mean, literally, we could do that. I don't know whether it'd be a good idea or not, but it'd be kind of fun. Maybe we'll do that someday. Who knows? Anyway, so back to jump. Now that we know the hole into which we'll fit, what's going to be around us in the simulation, okay, we're going to put it in the PC at the end, and we need to make sure that we judge the condition at the beginning and so on. Now we can start designing actually how we do jump, and it's going to be fairly straightforward now that we have pre-planned all of that stuff. So I'm going to turn off the PDF in OBS. Bink. So we can get to coding. So remember, we've got our 2 bops, which is going to handle the second byte, and the 3 bops, which is going to handle the third byte. And just for comparison, I've got to bring up what we did earlier, LXI. Loading a 16-bit value from the instruction stream into the PC is going to look a hell of a lot like loading it into SP now, isn't it? So we have jump.c. Actually, I'm not sure this guy even needs clock. Let me check this out. If I just eliminate it, so at the top, pound include i8080 impl.h. I'm going to just quiet down the compiler warnings for a moment here. Okay, that's still an empty translation unit. Fine. Whatever. So we look a lot like this move data into PC, but instead of SP, it's PC. Transfer of control, aka load immediate into PC. Well, that's only true of the jump instruction. The other instructions do a whole lot more, so let's not even make that a thing. So before I start, let's actually set the framework up. So we have jump and we have jump test. And I need to write a BIST. So that gives us just the bare minimum entry points so that we should be able to connect this up to the rest of the system. So inside main, let's hit the header file first. Inc i8080 impl.h. Wherever I have LXI, I'm going to duplicate it, and I'm going to put in JMP. And yeah, that puts it before dad. That's not a problem. So we should have jump init, jump post, jump pist. We have the opcode here, and there's going to be a whole bunch of conditionals. So op underscore j, we've got j and z, jz, jnc, and so on all the way down. So with that set, I am going to put in some prints. Well, I learned earlier these print top and print end, they were printing to standard out. Let's fix that. Let's use stub instead. I was using 3 stars, kind of set that up visually. I'll keep that. And stub prints out the function we're in. So let's we put this in here. We say print top and print end. And we're not getting into any of them because we haven't put the call in yet, but there we go. So now, let's see, i8080.c, source i8080.c, same macro, wherever we have jump, wherever we have LXI, put in the jump, and there's only the one place. And there we go, we're calling a init. So we know we are getting into an init at all the proper places, so we can take that out. Sometimes there's a small delay. It does. I do have this build thing running in the background that notices files have changed and does the build, but it doesn't happen immediately. I mean, it's not infinitely fast, so I can trigger this reporting thing. Report doesn't actually build. It asks for the logs of the most recent build. It does rerun all the benchmarks. So I get the actual benchmark values here, but it just reports the previous build. So if the previous build hasn't written those logs yet, we get stale data. Anyway, so there we go. We've got jump init going. And now let's come over here and let's look in test i8080 test.c. Oops, that's the wrong window. I want it over here. So wherever I have LXI, I am going to do this manually this time. Since I have to manually do the other code anyway. Okay, so now we have post and bist should be getting called. And there we are. We are getting into post, and we are getting into bist. Bingo. So there's that. So what architectural state do we need? Well, I don't think we have the W and Z register pair yet. So we are going to go back to inc i8080.h. And down here in all this auxiliary stuff, need to put a W and a Z, and I'm going to put them down here. So this, if we were using scummy little tricks with unions of structure, unnamed union containing a byte and a structure containing a bunch of bits, the fact that we have a Z register would have consequences because we also have a Z flag. So if I said Z, which one am I looking at? Kind of like how we have a carry flag, which is CY, and a C register. And all of the documentation for the 8080 calls the carry flag CY, even though I've always thought of it as the C flag. So that wouldn't conflict, but Z, there's no disambiguation there because W and Z were not visible. This is architected state, not programmer. Visible. Oh, I already commented that above. So Z is temp for low byte of sub ops. Okay, so we now have W and Z. We now need to make sure that they are initialized and all of that. So source i8080.c. So we're going to search for the IR, and wherever we have IR, I need to add something in for W and Z, like that. Okay, so we're initialized. Now at power on, we are stubbing these. This is the impossible to reach state. So this probably should be renamed. Now I'm going to reserve that for specifically real 8080 instructions that the simulator does not yet implement. So at some point we will have an illegal instruction handler where we will decide what to do when we get to one of the bona fide illegal instructions in the 8080. Some people writing simulators like this would say, well, let's go find some real 8080s and then presume that we can experiment on them and figure out what they do, and then presume it's useful to have a simulator that simulates one particular implementation of the 8080. And I don't follow that. I would rather have my simulator stop cold and say, oh, I'm simulating a generic 8080, and the generic 8080 has undefined behavior at this point, so we cannot continue the simulation. If then you wanted to simulate, say, the particular 8080 chip that a particular company was using in a particular product, at that point you'd then want to tune that, but we're not going there. Okay, so W and Z should now be set. Let's scan for IR again and make sure that we have put W and Z stuff in. Yeah, okay. So W and Z are now initialized. Now, similarly, we have some things that we do here during testing. So let's add W and Z to our testing things. So In reality, W and Z live in the register banks. They're up here with PC, SP, BCD, HL. The accumulator is out separate. I could reorganize these traces differently. However, this more closely matches the model of the CPU that the engineer will have in their head. So think in terms of PC, stack pointer, accumulator, and registers I can see, and then they'll go on to other things. So I'm trying to make this user-oriented rather than make it look like the block diagram. Although there is something to be said for simulations that draw a neat block diagram on the screen, then show data moving through the block diagram and across the wires into other boxes. That's kind of neat for a pedagogical example, but that's not where we're going with this. Maybe you could build something like that from this, but we're not specifically heading in that direction. Okay, so IR, trace init, we're going down here and we're going to do W and Z. And Finney, W, and Z. There we go. So we don't have any data coming out there yet, really, because nobody is actually changing the content. Speaking of content, source i8080.c, where we initialize these things. This means that I'm doing this data init of W and Z. So this is going to leave these data in their initial state. I'm not going to be setting them to anything specific. I think that leaves them in the Z state. Unknown. Leaves them in an undeterminate state. If we care about it in testing, we will set it to something in testing. They should never be used in a situation where they weren't previously set, because the only time we use them is in the actual instruction microcode where we are trying to bring things into WZ and do something with them. So yeah, there's that. We could, in fact, force W and Z into the Z state when we're done using them, so they would only show up while being used and they would go away. Not a bad idea. I could do that. After I latch WZ into PC, I can set them to Z and they will disappear from my display, and that'll be that. We won't have stale WZ data sticking around from prior stuff. It'll also tell me when I have committed it, when I haven't. So we are ready to go. We've got W, we've got Z, we've got our 2 bops and our 3 bops all set up and ready to go. Let's go back to our jump and our test. So I did something last time. I actually implemented some of the tests before I implemented the instructions, which turned out to be kind of useful. So let's look at the LXI test and consider how we would map that over. Actually, let's just take the entire test and work on it. So we have a jump test. Well, jump is not going to touch any of this crap. That goes away. Up, jump. And we are going to have some PC stuff. So I'm going to have 2 test programs. One is this guy who's going to do something, and one is the destination of the jump, which will do something. And the low byte is 0x55, and the high byte is 0x. Well, it needs to be within the ROM, doesn't it? I'm not sure how big the ROM is, but I'm sure the ROM is at least half a kilobyte. And then we're going to say op ___ ff, which I believe is the way I've done. Oops. I need to do an instruction that is going to be caught by the simulator as illegal. No, I will test the PC when I get back. There's the test program. And we're going to have another test program for 0155, which is going to do the same thing. It's going to jump back to 0155 over and over and over again. Why not? So in fact, let's just write test prog to 2 different places. So this is going to be cells into, well, PC we're going to need a lot of here. So we're going to say P adder PC is equal to CPU arrow PC. So this kind of assumes that the PC value is correct. Well, we're coming to this. We've been reset, so PC value should be 0. I'm going to assert that. Assert EQ integer PC arrow value. That's going to be the only place where I test. It's a precondition, and then we're going to weaken the precondition. Our precondition here is going to be precondition prog at OX0155 does not overlap image of prog at PC. So we have a weaker precondition down here. And we don't need to worry about that. And our test program is nop, jump, nop, nop, nop. This is a jump to 0155. And our expected result is that we are going to be at 0155. We're going to do a nop and a jump. And I'm going to just let it do that. Assert EQ integer. So we finished the jump instruction. Actually, architecturally, this value 0155 doesn't go into the PC, it goes into WZ. So what we really want to do is execute the nop after that, and we want to test here. So assert EQ integer OX0156 PC arrow value. So I'll execute those 3 jumps. Just because I think that will give us some interesting stuff. I can run, well, no, let's run that back. The jump is going to be a lot of machine cycles, so let's just verify that it's doing the right thing twice. There's our precondition. Again, this is a strong precondition this time. Into is not used. So now what we're getting here is, on the left, we can see the error. Should be visible to you. Aside from this warning unused variable, let's get rid of that. CPU in phase 1, so we're in the phi 1 rising. PC is 2, and IR is C3. So we have attempted to execute an instruction C3, and the CPU is going, wait, I don't understand. I just don't understand. Now, this gives us the phase of the T state. It doesn't tell us what T state we're in. But we do know that we're in an unimp. And that would be in T4 of M1, because T3 is where we vector to it. So, let's get back in here. What do we want this guy to do? M1T4 of op jump is equal to I8080 jump. I called these I8080 state M1T4. Okay. So there's the declaration. And now we implement. So M1T4, if we turn our PDF on, we need to plan this out. There we go. So jump instruction. So M1T4 does nothing, but it does arrange for M2 to be a 2-bop cycle and M3 to be a 3-bop cycle. So let's do those. So first off, can I just use this? I think I can just use I-8080 state 2-bops, which is stored there. So goodbye jump M1T4. CPU arrow state underscore 2-bops. So that's the M1T4 state that arranges for the M2 cycle to be a 2-bops. And so that will arrange through here through 2-bops eventually, deliver us in M2T3 to I-8080 underscore state underscore jump underscore M2T3. Yeah, I should have kept the other guy here. CPU and int phase. If I were truly in the swing of things, I would have this all set up as a nice little template that I would just instantiate here. So during M2T3 of a jump, what are we doing? Well, we're going to set the next state to be CPU arrows. Well, CPU state 3-bops T1, that's correct. So M2T3, we're going to latch the data into, and I left the PDF on the screen, so we're just going to look at it and then get rid of it, latch it into Z. PDF goes away. So here's our function that I'm working on here. And I'm going to say data to CPU arrow Z is, and it's the same thing we did here. So are we responsible? Yeah, we're responsible for dropping DB in and ZA out the address bus. So there's that as CPU arrow data value. Got it. So there's M2T3. Now 3-bops is going to have us back in M3T3. Now M3T3 is our last cycle. So, oh, almost forgot, I need to release wait as well. We check to make sure we're doing all the right things here. So the M2s, release wait, collect data, store the data, release DB in, release adder. M3, release wait, set the M1 return, collect the data, release DB in, and release adder. And during this phase, right there, I'm going to muck with PC. Right there during phi2 fall, we're going to say data to, adder to PC is going to get W high and Z low, I believe. Yes. Now, I do not trust operator precedence in the C programming language. And because of that, sometimes I forget what the table is. I used to actually have the table printed out and tacked to the wall next to me until I realized that anytime I had to look at that as a after a few years, as an engineer that had several years under their belt working in C, if I still had to refer to that table, then that was a good reason to put the parentheses in. Wow, my CPU fans are really going wild. Let me check my temperature monitors here real quick. Fans going wild, temperatures aren't too bad. Okay, so yeah. I am running under Linux and I have not really configured the fans to stay quiet, so we'll just have to have the hum in the background. I don't even know if you can hear it. I certainly can. So that should do the jump for me. It also helps if I make it valid C. So here this says unused parameter CPU in something. Forbids nested functions. Well, that's because I forgot a close brace. So this is going forever. No, it isn't. It's just going for a long time. Okay, so this test condition is failing. So after the NOP, this is now saying expected value is 156 and the observed value is 1. So this is not getting what I wanted. So M2T3 should be delivering to M2T3. Let's put in a print top and a print end. This is going to cause a whole bunch of output. Well, first of all, is the CPU going wild because something is still running? Yeah, probably what happened was that my program was just running in a loop. There we go. Okay, so here we are. Top end, so M2T3, top end. There's the three phases, top end, top end, top end. There we go. Let's take a look at the plot. There is no plot because we are bailing here. What I want to do is, for now, turn off the abort and turn off this guy. We no longer need to see these because we know we're getting there. So we're failing this condition and this condition. In both cases, our observed value is 1. So PC's getting zeros, guys. And there is our jump PNG. So, NOP. Then we get IR gets set to C3. Well, it's probably because we are writing to the Z register in both of them when the other byte needs to go into the I8080 jump.C. See, this is writing to Z here. Yep. So we weren't actually doing anything with W, so who knows what W had. So for the report stuff, I think I want to, no, I don't want to in general delete all the PNGs. I'll do that manually where I need them. Because if a PNG exists, I'm not regenerating it. Okay, so here we go. Jump, 5501 of the bytes coming in. And we see here that the PC goes 0, 1, 2, 3, 155, 156, 157, 158, 155. So we're getting back to proper, and it is running. So we have a jump instruction. But we're not done yet. So now we need to do the conditional jumps. So conditional jumps, if we can turn on the PDF again, differ from jump in one thing. During M1T4 and M1T5, we are judging the condition. And this takes the 8080 to T states. Why does it take 2 states to do this? I do not understand. I could understand if, in the case of a false, during judge condition, we would increment the PC 2 more times, and we would then not do these fetches. I do not believe that the conditional jump does that. Let's see, there's no footnotes of any sort. So basically, if you're not taking the jump, there's actually really no need for the processor to fetch those 2 bytes. Now, the logic to do this is a little more complicated, and it would actually take 2 T states to do this because you have to increment the PC twice, okay? But PC out status, what's the footnote there? That's a footnote 6. 6 says memory read subcycles. So here, footnote 12 says if the condition was met, the contents of the register pair WZ are output on the address lines instead of the contents of the program counter. So apparently, we judge the condition and we stash it somewhere in some latch somewhere, and then that latch is honored here on whether we are using PC or WZ for the address. Interesting. Very interesting. So really, this would mean that the instruction fetch code has a bit in it that says whether you use PC or WZ. Okay, code 13 says if the condition was not met, cycles M4 and M5 are skipped. Now that is specifically for the call condition, because we would not be writing our PC to the stack pointer. So with call is smart enough to skip these if the condition isn't met. But they are not smart enough to skip these fetches. Judge condition. I think I'm going to have an edge. I think I'll do this. I think I'm going to go ahead and actually model this bit of complexity in the 8080. We'll set up an edge called condition met, which is internal, which I am inferring is actually some latch in the system. I can infer this exists because it is carrying condition met all the way from M1, T4, and T5 all the way out to the M1, T1 of the next thing. So let's go do that. So include i8080.h. We now have another internal signal. It's cond met internal. Not named, but existence. So we have a conditions, we have a signal here who is not, they're not named in any documentation, but the existence is inferred from the document. Let's set up a source i8080.c bit of code that does it. We're going to look for this inhibit store. Inhibit PC increment is part of the interrupt code. I established this early on, and what did I do with it? I may not have it everywhere. Hold on, git grep and hpc inc. So yeah, we have it. I was anticipating what was going on, and I do not set it yet. So let's actually cond met int. I'm going to look at ret m1 int for my model on where to manipulate it. In fact, I'm going to move it up above inhibit PC inc. Okay, so here in init, we grab a pointer to the edge thing. There we go. So we have initialized it. Now this is normally going to be high, and it'll go low when we do not meet a condition. How about I call that something else? Call it fetch WZ. There. I'm going to call it after what it does because I'm absolutely not sure this makes any sense. This is normally going to be sitting at 0. This means that, oh, every instruction fetch, we're checking this signal. Fuck. So our choices are, every instruction fetch, we are dipping into memory to look at this fetch WZ and doing conditional branch. Or I duplicate my M1s. Or I have external. Nope. We're not doing this. We are not doing this. I will have to carry that by what t-states I'm activating. So I will have a series of t-states for we are going to jump and a series of t-states for we're not actually going to jump. So when we judge condition, the condition state will be held basically on which set of t-states we run. And we will be latching our final data back into PC where it can be used. Okay. Fine. So we have this for, we are actually doing a jump. I'm going to duplicate them for, instead of jump, this is, I call it JF. And the difference is here we are not logging it in there. So the other thing I wanted to do was data Z of CPU W and Z to kind of clear out W and Z for us. And we are not, since the condition was false, do not copy WZ into PC. There. Otherwise, these are the same things. So the only difference will be when we do the opcode decode of a conditional branch. Instead of going to 2 bops here, we're going to go and make a decision, and then we're going to deliver to 2 bops T1 with either this guy or this guy. Now, its IR is going to do the work for us. I'm not sure we can do this. Because 2 bops is only going to deliver based on the op. So either I have to muck with IR, or I have to muck with the jump table. I'll muck with the jump table. So yeah, we're going to end up writing into M2T3 and M3T3. We're going to write either the JF or the JMP. Okay, so self-modifying code, y'all. During the early 90s, self-modifying code was talked about in hushed tones as something that was sometimes needed, but really, really a bad idea if you didn't absolutely need it. So this is why I am considering it, and I'm considering it to be dangerous here. So let's start right off with our conditional jumps. Stepping the PDF forward, and I'm going to do them in the order that they're covered in the PDF, which I'm going to be off screen. Let's just put the order in here. It is JNZ Z equals 0. JZ Next set is no carry and carry. Conditions there are cy is equal to 0 and cy equal to 1. Next thing is PO and PE. This is P equals 0 and P equals 1. And then we have P and M for plus and minus. This is S equals 0 and S equals 1. So let me write one of these to begin with, and then we'll figure out how to macroize it. So we do JNZ of M1T4. What's it going to do? Well, M1T4 is going to be pretty stock standard. Let's grab M1T4, I8080 2 bops. .c. M1T4 does very little. Not responsible for much. In this case, it's going to be CPU arrow 2 bops T1. Buck with CPU arrow M2 T3 of CPU arrow So, unsigned op. Op equals CPU arrow IR arrow value. I believe op can come in as a macro parameter. Because we're going to have one of these for each opcode. So stuff set by the, so I have macro parameters right here. Unsigned op is equal to op JNZ. FB is going to be flag bit. And non-zero is going to be flag Z is off. Remember what I was saying about operator precedence in C? Now, the reason why these are confusing, the root of the operator precedence problem in C is that the bitwise and the bitwise OR operations, I believe, were initially pegged at the same precedence level as the logical amper amper and the logical OR. In fact, let me bring up, see if I can bring up that. So that is incorrect. However, the operator precedence table for the C programming language does have the bitwise operators are slightly higher precedent than the logical, but it's the bitwise and the logical are adjacent in the table, okay? Which means that the operator precedence of the bitwise operators relative to, say, equality checks is not what you expect. Equality is tighter binding than bitwise, which is very confusing when you start comparing it with, what would be the rational thing. If A and B equals C, It's actually if A, bitwise and with B equals C. How could they have known? Yeah, so we parenthesize things like this because otherwise it would put the parentheses elsewhere. So if that is equal, the alternative to mucking with these is actually to carry separate 3-bops or somehow allow 3-bops to select from multiple tables. I don't know. Okay, so that does that. It will set up the jump table for M2T3, so we'll end up either doing the jump or not, based on this condition. So our state is now embedded in our opcode table as we run for. So these opcode tables are not constants. Now if we compile it, we see that I forgot to do some things. And what I'm going to do is I'm going to try this out. This is JNZ. And I'm going to initialize the tables to the JF variant. Reason why I want to initialize the tables is so I have a record that this is in use. It will be overwritten anytime it is used, so comme ci, comme ça. Our jumps are already slow because they're taking all these extra cycles. So I think that adding this little bit of work in there is not a bad thing. So now we have J and Z as an instruction. And where did my terminal go that is running? There it is. Got it. Invalid suffix on, yeah. This is state, 2-bops T1. So J and Z, M1 T4, because it needs to be here, I-8080 state. And in fact, we need a T4, we need a T5 to get the right number of things going. So this is a JF M1, actually J M1 T5. And I believe all of our jumps can share this, since all it does is stall and send us out there. This says defined but not used, but it's actually used down here, which means that that was an old stale. So there it is. Here's our 4 declarations. Take all of this and move it down below jump init where it belongs. Uppercase. So even talking to myself, we are still subject to the telephone test. So M1T5 undeclared is a stale thing. There we go. Got to wait for the compile loop to finish compiling before I fetch the results of the build. So supposedly this is now hooked up. Let's go look at the test. Let's fork this out as a separate test. So jump is going to have a bunch of subtests it does. So jump bist is now JMP bist, JMP, and JMP bist. Actually, let's call it JMP. Okay, JMP bist is just the main entry point. Okay, JMP bist T. And oh, wait a minute. Can I put all these in one program? Call this test prog 0000. So I want a program that does a jump non-zero, and then the second time through it does a jump non-zero not taken. So this is 0, 1, 2, 3, 4, 5, 6. Let's put this at 10. So at 10, well, let's start off with op xra a gets us a cleared accumulator. Now INR, actually, what I want to do here, I want to do a decrement DCR, which will set the 0 flag if I decrement to that. So I'll DCR A. So we're going to start with 2 in the accumulator. We're going to jump down here to this guy. So this will test our jump. And here we'll just put a op RST 7. If we get there, currently it's not implemented. If we get an RST 7, I'll set that up specially, or maybe I'll replace this with something else. But we shouldn't get there anyway, and if we're testing our PC, we're good. No, we're not. Because we need to do one more instruction to find out where we ended up. So test prog cells plus 0x0000 gets test prog 000. Oh, 10 test prog at 10. So the first time through here, we should see sets to 2, jumps to here, decrement register, JZ, JNZ, falls through to there. So jump non-zero will jump back. Decrement register, jump non-zero will fall through. Okay, so NOP. And we're going to test here. So this could be 0101, 011. Actually, this is an MVI. So this is actually 012. So we either have executed this NOP or the DCRA. We expect to do the DCRA. This is going to do a JNZ, branch taken, and then a branch not taken, and it'll do the NOP. 10, 11, 12, 13. There should be 14, 15 after the NOP. Okay, so we have tests running and failing. First thing is that this is not a NOP. This is a MVI OX02. So this is the instruction is at 2. And this is not an MVI. This is a DCRA. So this is OX01. I believe 10, 11, 12, 13, 14, so 15 is correct here. Hey, how about that? That'll be an old jump. Let's get a new one. Okay, so we executed properly. And what do we see here? We see PC 0, 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, 10, 11, 12, 13, 14, 15. There we go. The accumulator goes from 7 to 2, 1, 0. So it came in with a 7. I am going to data Z CPU accumulator, just so that we don't have garbage at the front. Okay. So data implicit of data Z because it's lowercase. So we reloaded 210 and PC does the right thing. So there is our test of JNZ. Woohoo! So back to here. So how can I turn this into a macro? Well, those are our 3 values there that we need. So let's start off with pound define. And I'll bring up the LXI as our model for how we want to do this. name underscore M1T4. And what we want in there is the condition code is going to be this, like that. And defin of the same thing is static F8080 state name J M1T4 of CC. Then we say name J M1T4 for each of the opcodes. JNZ, GZ, NC, POPE, P, and M. And I go back and I just insert NC, C, POPE, positive and minus. That gets me all of those declarations right at the top. Token pasting is double hash. Single hash turns the following token into a string. So there's our token pasting version properly done. And these those become defins. Okay. So JNZ has to become J with a capital NZ. So we're going to do this. I'll call it J naught. There we go. Okay, so it'd be I-8080 state underscore JNZ. CC should be NZ there. Underscore M1T4 there. Undeclared here. Almost forgot we still need this guy. Except it's not that, it's F80 state this. Ha. Here's the tip-off, JJZ. There we go. Declared static but never used. Fine. That's correct. So now we need to turn this into a macro with op and flag bit and flag val, our parameters. And the macro op. I'm going to make the names shorter. Okay, well this is just that. Name JM1T4 of like that. As we saw over here, that gets ugly. Where did I fix that? Did I fix that in I-8080 dad? Yeah, I have the decal macros. Okay. So that's not going to compile, of course, because this is all supposed to be inside the macro. So CC, FB, and FB. There we go, FB. There's our op. Going either jump or J naught. Now let's see if I've confused the indenters enough. How about that? Yay! Indenter is happy. And now I need to actually expand this. Decal JM1T4. Impl, hold on. JNZ flags Z, and this is 0. JZ is flags Z is flags Z. Next two are NC and C. Then we have PO and PE. Hey, meow. Oh, we got somebody that wants to look at the code. Meow. See what we're doing here, Lucy? So, well, I've got a cat on my lap. Let's look at this and read it a little bit. Oh, you didn't want to be picked up? Were you just telling me that you got some water? I better go make sure she's got water. Be right back. Okay, cat break is over. Cat has fresh water now. And she's sitting in the door just staring at me. She didn't even go over to look at the new water. Of course she didn't. So what have we got here? Undeclared first use of the function. Did you mean op underscore JNZ? Well, this should be token packing op underscore J with CC. Op JJNZ. Oh, there we go. I did it again. This is the condition code, not the op code. There we go. CYS is a typo. Put the other instruction here. This is P and M. And this is flags S. There's all of our 8 conditional instructions. Okay, so here, this says JM underscore M1T4 defined but not used. Well, that makes sense because we're not actually doing that. So we need to grab these and hook them up to our various things. So starting keyboard macro, search forward for the // Grab that to the end of the line. Just keep that much. CPU arrow M1T4 of op underscore J that equal to I8080 state J that M1T4. JM M1T4 not used. It's used right here. Geez, I didn't wait long enough. So now I need to do the same things here for the other 2 tables. M1T4 becomes M2T3. And, oh, uppercase state is not a thing. Now, all these guys need to be just this J naught. Okay, so we now have all of the conditional instructions set up. And now the long boring part, test. We need to write a program that will test each one. So this tested JNZ. We're going to do something again. Nope. I think I can write this all as one program. I really should use the assembler to do it at this point. It is installed. So for instance, we have things like this. So I'm going to do jump test.asm. I'm not sure whether the assembler does that or not. So where did I put my LST files? I put them in here, didn't I? Well, obviously this is not compiling it, or not assembling it. I think I have to make LSTs, right? There we go. So this says I can't do 0F. I'll call it TJMP, so it's a target of the jump instruction. And what I'll do is I will encode a fail here with an RST7. No, I'll encode a fail with an RST0. So that way, if we actually implemented RST, that would push our address onto the stack and start us running at the beginning again. And this would wipe out our memory if indeed we ever did this. Okay, I'm going to revise my, let's see, bin loop says build says make loop. I'm going to make ASMs, LSTs, as part of that loop. And also it means that I need to get into live coding, bin, can you make file? Wait needs to also wait on the assembly sources. Which are ASMs. So now if I insert another NOP here, and that updates that, and there we are, there's our program. So, T-jump, I am going to write a test for J and Z. So this is MVI C, comma 2. T, J and Z is going to be DCRC, J and Z, T, J and Z. Let's make it a little more explicit. I want to have specific fail locations. So J and Z, this should be a jump not taken. J and Z fail. DCRC. J and Z pass. So there's our jump. I'll toss in a NOP here. J and Z fails. So if we jumped here, then we failed. And if we jumped here, we passed. And we're going to do 1. JZ fail and JZ pass. Now we need no carry and carry. So no carry, if it's 1, we decrease it to 0, there's no carry, and we do not jump. If we decrease it again, the flag is set, and we do jump. I will fix the indentation on that in a moment. We need something similar for JC. We're going to start with it at 1. No, we're going to start at 0. So if this jumps, we fail, and if it doesn't jump, we pass. JC, next thing is parity odd and parity even. We're going to start with this at 5 hex and 6 hex. So 6 decremented by 1 gives us 5. Five has even parity, so jumping would be a fail. We decrement it again, and we get a 4, and jumping would be a pass. Now I need something that decrements. Let's see. 6 to 5 doesn't change parity. 8 decrement to 7. So 7 has odd parity, so jump there would be a fail. And decrement again to a 6, and it has even parity, so we should pass. Okay. And then plus minus. The result of this decrement needs to be positive, and then we need to be negative, so we're going to start at 1. There we go. So if we encounter an RST0 at any time during this test, then we have failed. And if we encounter an RST1 at any time during this test, then all the tests have passed. Well, all the fails are really the same thing. No, because we fall into them. Okay, so yeah, I don't want to do an additional jump. I'll just let this be as it is. So there's a couple things we can do here. We now have this listing file. I could turn this into inline hex, or I have a way of loading hex data into a ROM, and we should probably do that. So we have JPE fail and JPE pass. We're in 2 places. Parity odd, parity even. What did I do here? JNZ, JZ, JNC, JC. J parity odd, J parity even. Yeah, I didn't finish my testing. Plus and minus, so PE is P. So jump plus. For this to work, I need the first jump plus to be a fail, so this needs to be negative. So 81H decrements to 80 hex, so JP should not pass, should not branch. DCR it again, it goes to 7F, and JP should pass. And now we do this again. JP becomes JM. 01, decrements to 0, negative should not jump. Decrement again, it becomes FF, and jump minus should jump. There we go. So, we have in our ROM, we have a way of loading a hex file. And these are in hex / whatever. Apparently my assembly isn't assembling the hex file into place. So what are the what's the command line here? ASM that -o obj / jump test. So it's putting it in obj. Well, that needs to be in the other directories. Let's fix the rule. Let's touch everything. Make LSTs. Now our hex directory has all this stuff in it. We're ignoring anything that we didn't explicitly check in. And there's our jump test hex file. So ROM has this load function we're going to use. ROM 8316_load of TS arrow ROM sub-0. Actually, this is just ROM sub-0. And base is the base name of, oh, this is the address of the ROM. And the file I'm passing on through the hex parse. Let's make sure hex parse isn't doing something wonky with the file name. It's just opening it. So this is hex / JMP test.hex. So basically, we're going to continue to execute instructions until we either see an RST0 or an RST1. So IR is either going to be, well, we're going to have a valid IR at the end of the instruction, right? Because we're not Zing at the end, I think. I hope we're not Zing at the end. Let's make sure. Live coding source i8080 fetch.c. I believe nobody ever Z's the IR. We'd have to do it before the instruction fetch, and yeah, we got this commented out. But that happens on Phi1 Rise. That's actually safe to do now that I think of it. So we haven't done the Phi1 Rise of the next cycle yet, so we should have the IR ready. So now we need appropriate messages here. So this is going to be, I think, fail. So assertion failures are a little more complicated. but we are going to use fail to do them. So at what points do I want to actually do the sig plot? Probably not the whole thing. Cells is not used. So we're going to get some test conditions failed on the ALU. Why? Why are we getting the test conditions failed on the ALU? What did I just mess up? So the only thing I did was Z out the IR fetch. Oh, that's right, because the ALU commits in T2. I8080 fetch.c. Comment. If we were to muck with IR here, then all of the code to commit ALU results in T2 of next M1 it becomes broken. No, messing with IR here breaks ALU right back in M1 T2. Okay, so now we have we're hitting an unimp. Of course, because the unimp happens before our failure here. So for this to work during this test, I need to override the opcode decode here so that actually we can get something going. And I'm going to do that. CPU M1 T4 of op RST0 is equal to I8080 jump test pass and jump test fail. Now, don't really have to do anything special. I'll just have these two tests, two cases. They will simply be a trap T state. And now I can actually do that. And that. Now we actually have to finish executing this instruction for this to happen. If we want to use test 1 instruction, which I'm not going to do. So instead what we'll do is we'll have a static I8080 jump test done equals 0. And for fail, I'll set it to -1. And for pass, I'll set it to 1. Now, instead of jumping ahead by 1 instruction at a time, this is clock run 1. This is while I8080 state jump. So one of these two is going to hit it. Now, I could do a different plot for each of the instructions. I just need to know when to do it. And maybe I would pick up a different, well, let's do it this way first. I may pick up another reset instruction to do a jump test next. I'm actually using CPU. So jump test fail hit at PC 10 hex. So jump test fail is an RST0. And we look at our jump test listing file, and we see that we are getting to that's not really helpful. It's going to print out the PC where we will next execute an instruction because the PC has already been incremented. So this looks like it's wrong. Also, we don't know whether it failed in one pass or the other. So we're going to jump to NZ fail, JNZ, it's going to be fail 1, fail 2, and let's fix all of the lineups on these guys. So if I do this, that'll make it clear what's going on. Even clearer if I just do that. There we go. I don't need all these extra knobs. Tabs back in. change colon, new line, tab to colon, tab. So there we go. So now we want to find all of these patterns here and change them to look like that. So $$ is in those places. So let's do this. Keyboard macro. $, this becomes F1, then F colon becomes 2 and 1. There we go. So label not found, JNC F1. 2F. 2F becomes F2. 1F becomes F1. There we go. Now it assembles properly. And we go back over here, and we do see we're still hitting the fail at 10 hex. We've got our LST file. So this says that this guy is jumping. Well, that makes sense because the test itself has a bug. 2, decrement, JNZ. We need to start out at 1. Decrement to 0, JNZ does not jump. Decrement again, JNZ jumps. Now we're hitting fail at 1C. This is JZ. And see what happened was I had that condition was somehow getting inverted in my head. We're still hitting it at 1C. So here, this JZ is not triggering. So it's 2, decrement register, and this is not jumping, decrement register, and this is not jumping. So when we are done running this, pass or fail, oh, this is an actual fail. So I'm going to say stub here instead. So it says jump test fail hit at 1C. So this is repeatedly hitting the failure at 1C. Bugger. We're running 1 clock. We're setting jump test done to -1. So we repeatedly hit it. Makes sense, but why are we not getting back to the run test loop here? Okay, interrupted by a minor cat-related incident. Again. Quit. Link live coding. GDB. Okay, apparently I was in the complete wrong directory. Okay, so back at the top of the output here, see we're doing a whole bunch of things. We have all of the normal output we get from our dist. Then we get right here, jump test line 57 done equals 0. Oh, here it is. Can't allow that. There we go. So we execute a whole bunch of these. So I can safely get rid of that. And I can turn my compile loop back on because it's not going to run infinitely. I can run the reporting stuff normally. And now this gets back to here. So we're hitting it at 1C hex. So this JZ is not behaving. But now we should have this image. So 1C PC buzz, 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 buzz. So C goes 1 to 0 to F, 2, 1, 0. So flags, the 0 flag should have been set when we got here. The 0 flag is written back in the T2 state. So what I'm going to do here, what I'll do is I will insert an RST3 at the top of each one of these, which will say, this is where we want to basically break the plot. Because I do need to see in a little more detail. So I see an RST2, I'll dump a plot out. At the end, I'll dump a plot, so I don't need this one. Say test page. And to make this a little more friendly so I don't get that problem when my tests do things, this page, I will set that M1 signal. And I'm going to force that on all of the calls I make to this guy, because we really shouldn't be continuing to call him. And it's okay. So now we need a test page. Modify the page string here. So this is going to be a memory leak. Format malloc a thing which it returns. We should be stuffing in a variable and calling free. Let's do that. You do need to cast it back to void fn to get rid of the const. Jump test page hit at, yep. So 5. So we're going to hit it 3 times, so we really only want to do this based on one of the phases. So I'll do the printing. I'm going to do the plot when we hit phi2 rise. Gives us a little bit of a margin on each page. And that means really for consistency, I ought to honor the phase in the rest of these. So suddenly, YouTube is saying it's not receiving enough video to maintain smooth streaming. That's bull. Unless something else is going on the network. And it shouldn't. Actually, OBS isn't receiving video very well either. So OBS not happy. We're caught up again. So I don't know what's going on with YouTube. I will continue here, hoping this is working. And it looks like I have problems in my Python because it's not liking what came out. I'm wondering if the file name needs to be... Yeah, let's leak the file name string. That is actually risky. I may be storing that string internally. So Python is saying we've got a list comprehension here, int x for x and tau range split. And it says draw from JSON file, from timing main, from module, invalid literal with base 10 is empty, which means there's something going on here. Log timing. Let's wipe that out. Let's just take a look at it. Now, if I trigger a rebuild, okay, that rebuilt. And this is not telling me what file I was reading, which makes it particularly unuseful. Oh, come on, what is going on here? There we go. So this is processing JMP page 109. 105 and 13. This is processing things in parallel, isn't it? Yes, it is. So if I get in here, and instead I say make plots, one at a time. One, 10, 100. Oh my goodness. Why is it doing so many of these? Oh, good Lord, check this out. Haha, that's a problem. Okay, that could be why my Python code probably isn't set up to handle empty files. Just a guess. So here where I have these things where I test, jump, test page, I need to clear that flag again so that we don't do it infinitely. There we go. And now we trigger the build again. Let's go into source here and test here. Going into jump. We're going into jump test. Trigger that. My build brand. Okay. So now we're not not trying to handle a huge number of empty plots. However, we are getting problems here, so we're processing bist mwrite.txt. Log timing. Bist mwrite. So this is saying something is weird on this. So tell range is 24483 space 7. We're getting this. Invalid literal for int with base 10, tick tick. That's garbage. Okay, well, here's something. Jump 1 does have an error in it, and it is showing. So if we have that, we're going to return early. And of course, because I'm touching the PNG files, it doesn't reprocess. We have to go back to doc img. Rerun this. It regenerates all the PNG files. And big surprise, everybody's okay except the ones with tau range. Let's do it again. So jump 2 has empty tau range, and jump 1 has empty tau range. The rest were okay. Oh, because the automatic stuff runs it in parallel, so it was going to be reporting weirdly. So jump 1 and jump 2 have empty tau ranges, which should not happen. We will continue to print that, however, as a safety thing. And now we can go back to our test. So none of our jumps showed anything here because they all had empty tau ranges. Now that might be because I'm not actually recording any data. So what else did I not do with my session code? So SS is that. Oh, I'm a Goomba. T0, tau minus T0 here. So if tau has advanced, which it should, then we're going to do something here. And similarly down here. So this claims I am writing the plots. No, I don't know why that was coming up empty. So the jump, we're not actually creating those images. Bench not made because of errors. So we have these towering. Why would those guys be coming up empty? So logs. Let's bring up a working. These files are length 0. Hold on. Oh, I do need to sigplot thinny when I do the init, don't I? Silly me. I forgot that that was a thinny for each plot. So now when we go back here, we now have jump 1 text is good. And there's a jump 1 PNG file. Sync dbn wait memread. Now, why is this not showing anything else? All the other, the CPU guy that calls me should be providing all sorts of other information at this point. So I've forgotten how to use my own packages, apparently. Not uncommon. You forget how to use some parts of your code while you're working on others. So sequence is sigplot init, plot segs, sigplot fini. Sigplot init, plot segs, sigplot fini. PC should be advancing and should be noted on this. So why am I getting a core dump here? Maybe that's what I need to look into, because, we're getting to an unimp. There we go, 1D. So 1D, so JZ here, so the JZ instruction is showing up as terminal. Which means it's something in how I'm setting this up. Okay, honest bug. JZ should be going to JZ M1T4. JZ M1T4 gets down here and says we're in phase 1. M1T5. M1T5 says 2 bops, says 3 bops. I need an explicit PC trace to find out what I'm doing here. I can set that up easily enough. So let's send the CPU in here. Okay, so now, before I start, I want to do source adder.c. I want to set up somebody to call him. This is addr on valid of CPU arrow PC. I want to call i8080 jump PC changed. Actually, I'm just going to call it with CPU there, like that. Invalid use of void instruction. So here's our address trace here. So that's going to do that every time PC changes, which is going to be early in the instruction, really. 1, 2, 3, 4, 5, 6. Get to here, and this is actually, it increments to 6 during this RST time. The other way I could do it would be to trigger it on, yeah, let's instead of jump PC changed, let's say dbn. Let's catch a dbn on the falling edge or rising edge. I really want to catch the data that we're capturing from dbn. I think I can catch it on falling. No, I can't. Because when dbn falls, no, it's not as a result of dbn falls that we Z things out. Rise. Okay, so still not consistently. Oh, the FF is because there's a wait state. That's just wrong. That is just wrong. There we go. So this gets us our trace as we're reading the data. So jump 0400 0. It's reading a 0 from 4. So this is jumping. Jump past. Good. So I'm reading this correctly. We get a D7, and we say page hit, and so let's look at it the other way. Reaching up with my finger doesn't really show up in OBS. So we write the plot for the first little bit of it. Now let's take a look at that plot. So what we should see here is, well, again, the plot is not showing PC changing. Why is this plot not showing the advancing of PC and all the other things that show up in an instruction? It doesn't have it either. So the ALU stuff has it. What is the ALU code doing differently? Plot 650. It's almost like so by the time we get down to LXI, something has blown up our plots. So something has broken our plotting during Intel 8080 testing. So let's go back and take a look at that from the beginning. I-8080 test. So reset post. Reset for testing. This is post. We want BIST. EIDI halt has PC and adder and so on. MVI has everything. MOV. Those look good. Then we get into ALU. ALU, BIST, add. We have it there. Let's skip down to the last one. Should be ALU compare. That has it. Ink deck. This is INR, which has it, and DCR, which has it, INX. INX doesn't have adder. So DCR, adder got frozen right there. And we got a type 3 encoded for STSTB, which is not something that I emit. So that one right there, ALU DCR, looks a little weird. No, it's not LUDCR, it's InkDeck. So let's take a look at what it says in the log in the trace files for those. So timing. So here's DCR. And that just says the normal stuff, so we're starting at that tau. In I8080 underscore BIST. Interesting that these log files are coming up with zeros. That means that no data was captured for those traces at all. This is truncated. So this means that we are crashing out of the test somewhere. It's not actually logging these files. It is possible at this point that I have too many files open if somebody is leaking file handles. So let's take a look real quick at SIGTrace. Do a fopen here into FP and SIGTrace init. And if it errors, we're going to get a big old error message and we'll stop. So we know we're getting all of our files open. We also know that our program is running to completion. No, we don't. We're not running to completion right here. Aborted, core dumped. So we only get valid trace output files if we actually terminate properly. So the fact that we got to this unimp is a problem. We need to figure out how we got to that unimp without information from trace, because we do not have trace. But that, now I understand why we don't have that data from trace. So let's go back to this listing. This absolute listing of what we're fetching. And we can look here starting at 14 hex, 0E, 02, 0D, CA1F, 00, 0D, CA20. This CA right here, for some reason, we are landing on that 20 rather than continuing on forward. That makes no sense at all, because that means we properly handled the first one and not the second one, which means it's the case where JZ is going to branch, I think. Okay, this branch did not get taken, so this branch would have gotten taken. Let's take a look at source I8080 jump.c. M2T3, M3T3, M2T3, M3T3. State jump, state J0, 2333. Okay. This is our second instance of a jump that should be taken, a conditional jump that should be taken. So J and Z worked just fine. It's JZ that's failing, isn't it? 1D. Yes, indeedy. So wait, ret M1. Wait, ret M1. I'm going to add a whole bunch of debugging here because I am somewhat confused. Data value into the Z register. Okay. C, dbn, adder. It's going to be something really stupid. It always is when it's this puzzling. So we have C3, read a 4 next to 3 bops T1, read a 0, signal at red M1. Okay, so these used jump. J says now this is 2 bops T1, we're doing to J naught. 3 bops T1, we're doing J naught. Signal M1. And then we're signaling at this and this, so those look good. And page hit. And we start at 14. 14 has move C2. And 0D, which is a DCR. And we say CA. That's immediately going to red M1. They're at 1.7. And 1F is a known opcode for us now, which means it executed a 1F followed by a 00. So, JZ, you think to do strange things to me. Let's see here. What did we forget? So M1T4 of JZ is going to use this state JZ M1T4. So I am going to put something in here. Say here, and I'm going to put it here. Actually, let's put this inside the condition. So we're now focused on this area down here. Which means that this M1T4, oh my goodness, look at this. It's something really stupid. It's a copy-paste error. M1T4, all of these, this entire table, where I was saying M3T3s, I actually was writing it into the wrong table. There we go. That's much happier. Okay, so it's not a very long test at the moment. And is it failing? Don't know. Let's start removing these stubs. The jump read, I'm going to leave that in place for now, but we are going to comment this out. These places where I printed here could go away. So we do have a test fail now. So we may have to put some of this stuff back in. 2C hex, which means we're getting here. Let's take a look at the last one printed. So here's the instruction stream leading up to the failure. So 2C is going to 2D. The C register was decremented to FF. And this is a jump non-carry. Hold on, is that correct? JNC, we do not want to take that, and we do want to take that. So 1 decrement to 0, JNC should not do it. So let's start at 2-2 here. 2, 3, 4, so we load a 1 into the C register. Okay. 2, 5, we do the JNC, 5, 6, 7, C has the 0 value. That's incorrect. Where are my flags? Flags are 4, 7. Decrement C from 1 to 0, the carry flag should not be set. DCR of a register, I'm going to just double check this. All condition flags except carry are affected. Oh, Greg. Of course this isn't going to work because I forgot I can't load carry with DCR. I believe I can do a sub immediate to do this. Okay, so we hit a unimplemented instruction at hex 25. Probably I haven't actually implemented SUI. Okay, so we are now got up to 0 to F. So J and C, jump if no carry, that's going to jump. So I need to carry on the first and not on the second, which means A needs to start at 0 on this test. And needs to start 1 here, so we did not take the carry on the first test. There we go. So jump test pass hit. So our jump test is now working because I have now done the proper things for the carry tests because the DCR didn't hit carry. In fact, I'm going to change the rest of them to use the sub C stuff. We'll move that into A. And I'm going to start right at the top with a mauve MBI C, 1. There. So C will always have 1. We'll start the accumulator at a value, and where we were decrementing, we'll just sub C from it. 0, so we get a carry on the first one. 1, so we don't get a carry on the first one. A 6 sub C, a 8 sub C. There. Test pass hit. I don't need to talk about that anymore. And we don't need to say we wrote the final plot. Okay, so getting jump working took a lot longer than I expected. That was a 3-hour session. But again, there were some things I forgot. For instance, DCR not setting the carry bit when you decrement past 0 was a little weirdness of the 8080 that I had forgotten, but I implemented it properly, and I'm glad I did that. I have forgotten that I didn't have the immediate ALU operations done, so we're not using those. We are taking over those 4 instructions, however. And I do want to restore them when I am done. And actually, these are saved. RST0, 1, and 2. Now, if we get down to the bottom of the test and we actually return I need to restore these. Okay. Now we can get back into bin timing. I can remove the processing. And in here we're going to say let's store that in fname. So we have 90 unimplemented instruction codes remaining, having done jump. So there's the files that we did not yet check into Git. And I need to explicitly check some of them in. So doc img git add -f i8080 underscore jump JMP star PNG. We don't really want the bin files. And the hex files, need to either delete them as part of clean or commit them. I think I'm going to commit the hex files in case the assembler isn't available, but I'm going to delete the bin files. So this is star.bin. And this means that under there, I need to have a rule for clean, which also does $rf of the bins files. Do I have that done anywhere? I don't have anything called bins. So bins are these guys, and this is actually in the hexter star.bin. Hexter isn't hexter. Where is it? Haha, I didn't have hexter because I just wired it. Okay, so asm lst hexter is hex. Okay, so that leaves us with the hex files. We get our bin files cleared out with make clean. What do we have left that we haven't checked in? We have some log files. That's normal. Obj, the These files are left over from previous, so I can do a get clean -dfx. Then I could do a make world. Get status. And all these files were already staged, no changes since they were staged. And I modified makefile.rules. Okay, that's a lot of files that got touched, isn't it? So let's take a look at this and get cracking before I commit it. Yeah. Takes a moment for it to come up. Now, sometimes Get Crackin' thinks this is a private repo because I actually have peer repos on this machine, and sometimes I will push from my repo to them, and it says, oh no, this is a private repo. We can't do this on the free edition, but this is all on GitHub, honest. Okay, so there we go. 84 files changed. So we have some that are added. We had changing to timing. We have a whole bunch of PNG files that got rewritten for trivial reasons. I'm really not sure. Best of A. Yeah, I'm not sure what the difference is between the PNGs, and it's not really that important. So we now have all of these PNGs for the jump files. Oh, I probably inserted something. I bet you it's something like IR getting modified. Let's see, BIST intact, that's really the simplest one. Data's the same. No, I seriously have no idea what the difference is there, because those two images look the same to me. We have hex files we're now checking in, including CPU diag and Figforth probably already got installed. So 8080 got W and Z registers. We documented why that was commented out. So messing with IR here breaks the ALU right back in M1T2. We implemented jump. We removed the clock.h from LXI because it wasn't needed. This is not something I want to check in. And we need to discard that hunk. And having done that, I need to make sure we're still good. Testing is still good. Test gets that stuff all set up. And we're good. So add JMP and JCC instructions. And it occurs to me as I'm typing this that the jump versus non-jump for the second byte, the M2T3, that doesn't need to be modified because those two functions are the same. I don't know why I did that. Maybe I was thinking not storing it in a W or Z. Yeah, be that as may, we're passing tests and we're good. So we're going to say changes. Handlers for the conditional jump in progress based on whether the condition is met or not. Note, could unify M2T3. And that's it for this session. Pushing it to GitHub. And I'm going to call this a completed session. And I'll see you in the next one. Meanwhile, keep it small, keep it fast, and keep it safe.